Thanks for the introduction. Hello, everyone. Today, I will introduce our work, Empirical Validation of Commodity Spectrum Monitoring. This is a joint work with my colleagues and advisors from UC Santa Barbara, Ibo from Microsoft Research, and Xia from Dartmouth College. Radio spectrum is a precious resource. In order to use the spectrum efficiently, the FCC is developing dynamic spectrum access models across frequencies. In this model, there are two types of users, primary user and secondary user. The primary user has the highest priority, and the secondary user must use the spectrum without interfering with the primary user. For example, when the primary user is in an idle state. So, how can the secondary user detect the primary user's presence becomes a problem. To solve this, FCC applies spectrum database. Primary users will register themselves into the database by reporting the location and usage information. In this way, secondary users can easily identify the available spectrum by querying the database. And this makes the life of the secondary user much easier. So clearly, maintaining an accurate spectrum database is critical, but also challenging. This is because, first, since the information is reported by the primary user itself, we must check the accuracy. And in fact, recent studies have shown that over 30% of the self-reported entries are inaccurate. Second, primary users are likely to move. And as they move, we must update the database. So this means that we must monitor the spectrum usage on the fly. To do so, today, FCC gets a truck and drives around. The truck is huge, and there are a lot of specialized equipment carried in this truck. The device is expensive, and we also need a dedicated driver. So together, the high cost makes this approach difficult to scale. And also, the measurement coverage can be limited by the vehicle route. Clearly, this is not enough. So here, we propose a very different approach called commodity spectrum monitoring. So instead of using the large specialized device, we use commodity smartphones with embedded spectrum sensor. This is cheap and can be easily carried by the mobile users. And instead of using just one trunk driving around, we leverage the crowd. And here, users will use their smartphone to perform the measurement. And the participation can be incentivized by the network providers. More importantly, crowdsourcing can scale in coverage and measurement frequency. However, such a system faces two challenges. First, since the measurements are contributed to the user with a low-cost device, there could be large sensor noise and human artifacts. And the artifacts are too complex to be handled by the basic noise removal. And second, our system relies on the user participation. Then how could we get them to participate? One particular obstacle is that sensing will cost power. And if the power consumption is high, users may not be willing to participate. So with these challenges, many of you may ask, does commodity spectrum monitoring really work? So in this paper, we empirically studied the variability of commodity spectrum monitoring. We implement the proof of concept platform and consider the transmit localization as a monitoring task. We first look at the techniques to evaluate the data quality and improve the localization accuracy. And then we perform detailed energy analysis to understand and then reduce the end user cost. In the rest of the talk, I will go through this one by one. First, let's look at the measurement platform. Ideally, the platform should be just a single smartphone, where the spectral sensors is already embedded inside. However, there's no such a device available today. So here, we build the proof of concept platform by connecting the RTL dongle to the smartphone through a USB cable. The RTL here will behave as a spectrum sensor. It is cheap, lightweight, and can operate in the frequency range of 52 to 2200 MHz. It can support a max sample rate of 2.4 MHz. And in fact, it is already being considered as a potential spectrum sensor by FCC. The smartphone here will behave as a data processor. It will translate the raw data into received signal strength. We implemented Android app on the smartphone to collect time, GPS, and RSS tuples. Then we perform the real-world measurement. First of all, we set up our own transmitter so that we could have the ground truth of the transmitter's location. And here we choose 2 TV white space that are not used in our area. We did extensive measurement in 4 different outdoor environments from our campus to downtown. And these environments represent the scenario where people do their daily outdoor activities. And together, we had 48 volunteers to participate in the measurement. And they contributed to 17 hours data with more than 360,000 time, GPS, and RSS tuples. Now we have a lot of data. Then, we first did a basic analysis to look at the data quality. Here we observed that there's huge inconsistency across the measurement. And here we found there are 4 key sources that lead to the inconsistency. First of all, being a low-cost sensor, RTL has large noise across device, time, and frequency. Second, dynamic context in both the environment and the user body posture can generate sudden change to RSS. And third, interference signal, when present, can be aggregated into the RSS. So the first 3 factors will lead to the noisy RSS data. And last, the uncontrollable human mobility can generate measurement coverage bias. So now we want to know that what's the impact of the inconsistency? So here, we partition our dataset into snapshots of 5 minutes each and perform the 5 popular localization algorithms. The results show that the localization is inaccurate, and the max errors can be over 100 meters, which are significantly larger than the FCC requirement. So clearly, the data quality is a big problem. So here we propose several techniques to deal with it. First, we apply data denoise to mitigate the dynamic context impact. The high-level idea is to partition the data based on different contexts, and then we will process them independently. Second, we recognize that when the measurement is really bad, that will be impossible to clean it up. So here, we predict the localization accuracy. And this allows us to determine whether to use the data. If the data is really bad, we are not going to use it, and we will redo the measurement. And then we also extend the above designs to cases when there is interference and the wideband monitoring. However, due to time limit, I won't talk about them here. If you're interested, please see our paper or talk to me afterwards. Before presenting the noise handling approach, let's first look at the localization algorithm. In our case, we choose the widely known echolocation. The high-level idea of this approach is to capture the RSS link correlation. In ideal case, for any measurement pair, for example here A and B, if A is closer to the transmitter than B, then the RSS of A should be higher. One important metric used in echolocation is the satisfaction rate. When given the transmitter location, it is defined as a ratio of all measurement pairs that follow the ideal correlation. So, echolocation will first compute the satisfaction rate at each transmitter location candidate. And then the one with the highest rate will be the localization result. Compared with other methods, this approach is more robust against noise and coverage bias, and it doesn't require a large amount of data. So our approach will reuse echolocation. But instead of just applying a single round echolocation on all the data, we segment data based on different contexts. And this is because the context changes will break the RSS link correlation. Here's an example. When the user is walking around. In this figure, the dotted line represents the link distance to the transmitter, and the solid line represents the RSS value. So at the beginning, there's no context changes. And here we see when the user is walking away from the transmitter, the RSS is decreasing. The correlation holds. However, when the user changes its orientation, the user body blockage will change the RSS significantly. And this breaks the correlation. And as the user walked behind the building, the RSS also changed. And here we see the correlation changed even more. So if we blindly apply echolocation across all the data, the result will be bad. To solve this, we first partition the trace to maintain the RSS link correlation. To be specific, if consecutive RSS values differ above a threshold, we will segment the data. And then we apply echolocation and compute the satisfaction rate on each segment. Last, we aggregate the result across the segment to get the final estimation. So to see the effectiveness of segmentation, we tested on the cross-sourcing dataset. We compared with original echolocation and as well as the biased result of 5 algorithms. And the same, we partition our dataset into snapshots of 5 minutes each, and here's the result. Here we see that the segmentation largely reduced the error. However, we are not happy with that, because the max error is still very large, which is significantly larger than the FCC requirement. So how can we solve this? To cut the tail, one possible solution is we could just ignore the measurements that are not good enough to generate accurate results. And then we will redo the measurement. To do this, the first thing we need to know is whether the localization result is accurate. So here, we leverage the satisfaction rate heat map to predict the accuracy of localization. The heat map contains the satisfaction rate across the sensing space and is centered as the estimated transmitter location. Here we first show what the heat map looks like for the ideal case. By ideal case, I mean there's no artifact. The measurements are evenly distributed around the estimated transmitter location, and the RSS is free of noise. We can generate the ideal case based on the signal propagation model. And here we see the center has the highest satisfaction rate with 100% satisfaction rate. In practice, the structure of the heat map generated by the measurement is different from the ideal one. And interestingly, we found that the heat map can capture the artifacts like noise and coverage bias. Here we show two examples. In the first case, the localization error is only 13 meters. And in the second case, there are more artifacts and the error is over 50 meters. And obviously, we see the heat map of the first case is much more similar to the ideal one than the second case. So by capturing the difference with the ideal heat map, we are able to predict the accuracy of localization. So for each snapshot, we define the fidelity as a correlation between its measured heat map and ideal heat map. To be specific, at any point in the two heat maps, we first calculate the cross-correlation between the values at this point, and then we average them to get the final result. In this example, we get 0.7 for the first case and 0.5 for the second case. Then we test it on the whole cross-sectional dataset. And here we plot the localization error as a function of fidelity. From the figure, we see there is a clear pattern that higher fidelity tends to have more accurate results. And we can leverage this to make better decisions. There are two ways to use the fidelity. First, for the current snapshot, if the fidelity is less than a threshold, we're not going to use it, and we will redo the measurement. However, the threshold is hard to define. So here we propose the fidelity-based aggregation. So first, we will partition the snapshot into several sub-snapshots. And on each sub-snapshot, we will apply localization and get the fidelity. And then we will combine all the results by using fidelity as a weight. This approach is probabilistic, and good measurement will contribute more to the final result. So our approach will leverage the segmentation as well as the fidelity-based aggregation. We compare it with original echolocation and our method without aggregation. From the figure, we first see that the aggregation could have further improvement of the localization accuracy. And by comparing it with original echolocation, we see the improvement is significant, and especially for the max error. Now it's around the FCC requirement 50 meters, and which is half times smaller than the original one. Now, we could have accurate localization results. Another key concern is the energy cost. So here, we first analyze the RTL power consumption based on the measurement, and then we reduce the energy cost by duty cycling. First, let's look at how to measure the RTL power consumption. Active RTL draws power from the smartphone. So by connecting the smartphone to the monsoon power monitor, we are able to get the power consumption at the smartphone side. So we first measure the power consumption when all background activities are disabled, the screen is turned off, and the RTL is untouched. We use it as a baseline and subtract it from the forwarding measurement to get the actual RTL power consumption. To study the impact of duty cycle, we fix 10 seconds as a period and vary the duty cycle from 1% to 100%. In the rest of the measurement, we all tested on the Galaxy S3. First, let's look at the RTL power draw. The figure shows the instantaneous power draw over time of 1% duty cycle. Here we can see that there's an extra initialization phase which lasts about 1 second and a 100 millisecond tail phase. Both of the phases exist in different duty cycles, and they depend on the hardware. And aside from the two phases, the active state draws about 1.5 watt, and the idle state draws about 450 milliwatt. Then we look at the battery life when collecting the measurement at different duty cycles. We turn on the GPS and run the Android app. The figure shows the battery life of Galaxy S3. So here we can see that lower duty cycle could save more energy. But with further reduction of the duty cycle, for example here, less than 10%, the improvement is marginal. And this is because the GPS component is not duty cycled, and together with the initialization phase, they consume a large amount of power. And recent studies have shown that Wi-Fi sensing can be used to locate the Wi-Fi transmitter. So here, as a reference, we also measured the battery life of Wi-Fi sensing. Here we see that the Wi-Fi sensing consumes much less than the RTL, even with 1% duty cycle. However, there's possible ways to further reduce the RTL power consumption because better RTL models are coming to the market. Well, duty cycling can save more energy. It can also make the localization result worse due to the fewer measurements. So here, we study the trade-off between the energy cost and the localization performance. The figure shows the battery life and the max median localization error. Here we can see that, compared with the other point, the 10% duty cycle is a relatively good sweet spot. An interesting question is, how can we find the right duty cycle value? And we will leave it as a future work. So to conclude, we first empirically studied the viability of commodity spectrum monitoring. We implement this proof of concept platform by using smartphone and RTL. We propose several techniques to deal with the problems in data quality and energy cost. Our results show that using the low-cost commodity device could be an effective approach as the baseline of spectrum monitoring. And as for future work, we first plan to extend our method to newly improved RTL models. And then we will do larger-scale experiment to detect the actual primary user transmitter. Thanks for listening. I'd love to take questions.
Questions? No questions?
Phil, Stanford University. Could you go to slide 22? Is that a question about the power draw? So what you're saying is if I have the GPS on and the system is limited to 8 hours? So it's like, really that, I mean, so how much is the GPS?
It's
drawing?
with the GPS.
What's that?
It's with the GPS.
Yeah, with the GPS,
Yes.
yeah, but like that's a pretty, do you know what the power draw of the GPS chipset is off the, I'm just trying, because it seems like that's a really big number, right? And so.
Yes, when the duty cycle is low, when we have the low duty cycle, the GPS really consumes a lot. And I think it's around 400 milliwatt.
Oh,
Yeah.
okay, great, thanks.
Sorry, I have a question regarding the fidelity. So you define fidelity by using cross correlation, right?
Yes,
With the ideal case.
yes.
So what if we have a result that's very, very accurate, that's only a little center part have a very high value, everything else was low, then it also doesn't have a highest fidelity, right?
Right.
So why do we use cross correlation at the beginning?
You mean the cross correlation at just the center, or a
Yeah,
small
I mean,
size?
So why do we use cross correlation as the fidelity measure?
Because we want to capture the difference with the ideal heat map. We just want to capture that. And cross correlation is a very basic function, you know.
So why not we just integrate over the value? So if the only a very small case has very high, a very small case, very small error is 1, the other error is a smaller value, we just integrate over the entire figure to get a function, maybe that would be better.
Actually, we didn't try that. Probably we can try it in future work.
Okay, we can discuss that offline.
Okay.
Okay.